¿Quién lo va a presentar? Carlos.
El Carlos. A la Alicia.
Yeah.
Carlos.
Present her.
Ese cambió la letra.
Es un caso perdido.
Okay, can you put in the presentation mode, Marta?
It is on presentation mode now.
It is?
Yes. You don't see it?
Yeah, because we are watching the two parts of the screen. Next slide also. While I'm watching that.
Just a moment. I don't understand what has happened.
Okay. So I'm going to introduce you to start. Okay, we are going to start this conference and we are sorry for the delay. We had some troubles on the operation, but now we are ready to start. Now, it is a great pleasure for me to introduce Dr. Marta Molinas, who is a professor at the Department of Engineering, Cybernetics, and in the Faculty of Information Technology and Electrical Engineering of the Norwegian University of Science and Technology, NTNU, since 2008. She has worked for 15 years in the field of power electric stability analysis and is now transitioning into a new field, signal analysis and application to biotechnology. She is currently focused on EEG signal analysis and the EEG inverse problem, and gradually extending her research into biological signal, specifically EEG signals. For that purpose, her group is developing both computational models of the human brain to solve the neuromagnetic inverse problem and generic platforms for the analysis of non-linear and non-stationary signals suitable for physical and biological systems, electrical networks, and EEG signals. We have the honor to have Professor Molina with us to deliver the keynote speech titled, The Augmented Human Brain Control Devices. I leave you with Professor Marta Molinas.
Thank you very much, Carlos, for the introduction. In this talk, I will tell you about our interpretation of augmented humans and how this can be used for brain control devices. Human augmentation is not a new idea. It has been used always in different forms. For example, for neurological effects, humans have been using caffeine, tobacco, and alcohol for enhancing certain psychological conditions, for extending locomotion, all kinds of vehicles has been used, and for expanding the memory capabilities, computers have been used. So in this talk, I will take you somewhere into the future where human intentions and wishes can be directly translated from the brain into the environment to bypass the manual control or remote control devices to control our environment directly from the brain signals. So today, as I said, we use computers and we use a smartphone or some sort of remote devices to control our surroundings, where the user's will or the user wishes are implemented actively by using the hands. However, if we can decode the brain and read the intentions and the needs of the user directly, we will be able to open a direct path of communication between the brain and the environment, the devices that are in the environment that surrounds us. So the question is that, is there a difference if the tool is in our hands or it is in our brain? So this leap or all this that I am saying will be possible if by merging the powers of microelectronics, neuroscience, and artificial intelligence by using the processing power of computing in the clouds, and will materialize in many simple tasks and actions that will be able to help people in everyday life. In the following slide and 1 minute video, I will show you an example of an experiment in which we are trying to decode the mechanism of the brain to identify unique signatures of the primary colors, red, green, and blue, and use this unique signature to act as a command to actuate devices that surround us. And all of this can be done with the help, as I say, of artificial intelligence and machine learning, microelectronics, and of course, brain science. So in this slide, you can see a student that is using EEG headset in a dark room and looking at the green and red color that are displayed in a screen. And the idea of this experiment is to try to identify the very unique signature of each of these colors in the brain and use this signature as a command to actuate devices in the surrounding. So now comes the 1 minute video. And here. So if we can see that this very simple command that is shown in the video, we are using the green and red color because they are very simple colors that are associated with access control, with the traffic lights type of stop and go commands. And by decoding these two colors, that everyone that has good sight can see, the brain can directly send commands to control, for example, the lightnings, the internet, the screens, the thermostats, the window shades, and the alarm systems in a house. So this can be used, for example, for controlling, for in-home automation, for thought control machines. can be particularly important for the elderly, for monitoring this high-risk population. They can use their brain as long as they are healthy. They can use the brain or the eyes to control devices and transfer their intentions directly to the appliances surrounding them. It can also be used for early diagnosis and intervention. I'm going to show you an experiment in which we are using the brain decoding for security access in buildings and airports. Can be used in ICU, critical care, and in neurofeedback. All of these, for being able to materialize these applications, we need electroencephalographic device that is simple and that can be used 24 hours per day, can be highly portable, but also it needs to have a research grade quality on the signals. So we need to increase the ability of the EEG to extract signals of significance to be able to implement this the decoding in these applications that I just presented. Today, to access the brain and to access information of reliable quality in the brain, we can mention, for example, the magnetoencephalography, the magnetic resonance imaging that are very bulky and very expensive devices and not accessible for the large part of the population. And they are definitely not portable. The next candidate that we have is the high density EEG, which is non-invasive, but still is not accessible to large part of the population and is only being used for research. And we would like to bring up a new type of device that can be accessible to everyone, highly portable, and that can incorporate neuroimaging in it. So this is just artistic vision of what we are aiming at. It looks like a headset, as you can see the device on top, right? It's a headset in which we imagine to having the electrodes on this lace around the head under the lace, and this headset can have the freedom to move over the scalp to be able to have a good coverage of the scalp to have the same benefits of the high density EEG. So, and this brings us to the David and Goliath project, which is where we are proposing this device that I call it the Flex EEG, in which we want to get the same quality of signals and the same quality of brain source reconstruction that high density EEG offers, that we can see here on the left figures, on a much simpler device that has a few electrodes under this lace and that can move over the scalp. So I will present you some of the examples of experiments that we are running now to be able to promote this device with fewer numbers of electrodes. And the first one of them is the subject identification. So we're trying to move from fingerprints to brain prints. So the idea of this experiment is to use a neuroparadigm or a simple task that can give us access to very unique signatures in the brain that can identify subjects with very high accuracy, and can have promising applications in the intelligence services or in the access control in airports and access control in any buildings that has handles sensitive information, can be in hospitals and colleges, universities, banking systems, banking institutions, and so. I will show some results of these experiments that we have been carrying out over this last year. And the next one is sex identification, which is just a subset of the subject identification that we are already taking. running experiments. So with the same experiment, we can identify also unique imprints or unique descriptors of the sex of the person of which we are taking the EEG signals. So how we are doing this is that for the subject and sex identification, we start working with a high number of electrodes, can be with 36 electrodes or more. We take individual signals under a designated cognitive task, and we use this to build the models. We build models for the subject classification, or we build the models for the sex classification, and then we divide into subject group, male group, and female group. And then after that, we take this first is taken offline, and after that, we take some individuals from the same data set, and we test our models by using these individuals, and then we can test the accuracy of them for subject identification or for sex identification. And for electrodes number 14, we obtain very high accuracies for the subject identification and also for the sex identification, which these are not the latest results. I will show you the latest results of this. We have improved that. But now for promoting this lower number of electrodes, we start reducing the number of electrodes in this experiment until we get the lowest number of electrodes that will give you acceptable accuracy. So we repeat experiments until we get the same accuracy or with high number of electrodes. And we do the same testing procedure of the subject model and sex classification model. And we can obtain very promising results of high accuracies with even 1 and 2 channels, or 1 and 2 electrodes that can be sufficient to identify the subject and the sex of the individual. The current progress of this research is that now we are using resting state of the brain and the visual P300 paradigm to test the individuals, and we collect the data by subjecting the individual for 10 to 20 seconds of data collection, and then we test the person just by using 1 or 2 seconds. This has given us accuracies of 100% in a small data set, on a small data pool here at the university. And we have tested with much higher, with very high accuracies, but not 100%, in available data sets in open data sources, for which I will show you some results here. These are the results of a data set of 26 individuals in which we use the P300 neural paradigm and genetic algorithm and a support vector machine for classification. And what you can see in the vertical axis is the number of channels, and here is the rejection rate and the acceptance rate for the individual for classification of subjects. And this is the Pareto front. These are all the candidate solutions and the Pareto fronts you can see on the right side. And you see that the points of the Pareto that are on the upper part of the graph corresponds to the higher number of electrodes, while these here on the bottom are for the very low number of electrodes, and we can find a solution that can identify the subject with just 1 electrode, which is this point. And as you can see, this is a very high level of accuracies. We can improve these results even more if we use these results corresponds to a data set of 100 individuals. Is online data set. It is not our own recruitment. And here you can see again the channel numbers going for high number of channels, low number of channels, rejection rate and acceptance rates. Here in this area are concentrated the highest values of rejection and acceptance rate, which you can see projected in this graph. You can see the green points here corresponds to the highest accuracies for identification, and the result of the locations in the brain of these electrodes are given. We do a tenfold cross-validation, and for each of these tenfold cross-validation, we get the position, 3 consistent positions of electrodes in the brain that are sufficient to identify the person. So one is in the occipital area, one is in the frontal area, and one is in the temporal lobe. So these are promising results, and we are now preparing for collecting our own data with a group of 100 individuals working with the intelligence department of Norway, and they are very interested in the possibilities of these results. So in the future, we will get newer results with a real collected data from ourselves. In the next, I'll just give you a brief introduction to another application that we are envisioning, which is a light detector. Light detector has been presented very many times through history, and there are some of the solutions are based on blood pressure. Now we would like to present this that is based on brain signals. And we have already designed an experiment protocol for detecting when a person is lying, and we have some preliminary testing which they show good results of detecting when a person is lying or telling the truth. This again can have very promising applications in the intelligence industry and the judiciary systems. Another very interesting application is the alcohol detector. Alcohol detector can have promising applications in driving. Today they are using breath analyzers, and the breath analyzer is basically using based on the content on the presence of alcohol in the blood, that it can be detected through the breath. Here we are proposing to use the brain signals, and our hypothesis is that alcohol will remain, the imprints of alcohol drinking will remain for a longer time in the brain than in the blood. This can be a complementary test that can be used for detecting or for controlling people that are driving after ingestion of alcohol. Also in this case, we have some preliminary tests in our lab, and that shows some promising results. Today I'm not going to show these results. I'm going to now introduce you to the second type of explorations that we are doing for investigating the concept of the flex EEG with reduced number of electrodes, and how brain imaging can be incorporated in a device that has very few number of electrodes and be of high quality. So we have tested here electrode reduction based on the biophysical model of the brain. In here we have sources. We use in our model 8,000 and more sources, and you can see the red spots, the green and the black, they represent the solutions of brain reconstruction when we use 32 electrodes, when we use 16 electrodes, and when we use 8 electrodes. So in the next slides, I will show you, explain you the results of this. This is the results of the reconstruction errors. You can see in the vertical axis the reconstruction error, or the localization error of the source. And here on the horizontal axis, you can see the number of electrodes. So as I mentioned in the previous slides, we are reducing from 32 electrodes to 16 electrodes and to 8 electrodes, and we compare two methods here. The multiple sparse priors method directly applied to the source reconstruction, and a combination of a pre-processing signals that is called the multivariate empirical model composition that is pre-treated before proceeding to the inverse solution for source reconstructions. And we can see here the interesting thing to look at is these results of the 32 electrodes with the MSP here, and the 8 electrodes with this yellow bar, the 8 electrodes with the method that includes a pre-processing. They have almost the same source reconstruction error. So the accuracy level of these source reconstructions is equivalent with 32 electrodes or 8 electrodes. So with this, we are proving that we can effectively reduce the number of electrodes, which is reducing the amount of information and selecting the unique information or the most relevant information from the brain signals from the electrodes to achieve the same results. So this was one of the most important results we obtained in the last years that support and give us a promise that this flex EEG concept can be realized. So this is what we would like to get into the David and Goliath project, to have a headset, an EEG headset that is flexible enough that with a few number of electrodes, it can acquire the same quality of signals that the high density EEG can acquire. Here is a conceptual, or say vision of how this device will work, and we would like to make it accessible to everyone, and something that it is today happening with a blood pressure measurement device that one can go into a pharmacy and buy, or a oximeter device that one can go into a pharmacy and buy. The same we would like to get to say about this flex EEG. And it doesn't have to be the final design, but it has to be something highly portable and accessible for people, and could work with the smartphone, so that people can, so that the applications and can reach widely in many spheres of life, not necessarily only in health or in subject identification or access control. It can also be in the game industry. It can be used for enhancing the capabilities of the brain, for many different applications that will come also when people start using it. So in this slide, you can see how we envision that this headset will move over the skull to capture the signals that are needed to obtain the same quality as it is obtained today with the high density EEG. And towards the end of this presentation, I would like to share with you some of the augmented human experiments that we have been running at NTNU to prove how this can work in real life. This is just an experiment that was done for showing the students how they can use the brain signals. And this is one former student of mine that is operating and flying a drone with the brain signals directly. And here you can see an experiment done some years ago, in which the student sitting here is taking off this. There are 4 movements that are controlled with the brain: the take off, flying straight, landing, take off again, and flying backwards, as you can see here. And this experiment is rather simple, And to prove that, here is a child, my daughter, that she's flying this drone herself with just 5 minutes of training by my student. And it's something that we use for demonstration to students, also for attracting students in this area of science, which is a very highly multidisciplinary area. We cannot do it with just one science. We need 4 disciplines together to work closely to achieve this. So in the next experiment, I will show you another student. This was a master thesis that the student is playing Tetris, the game Tetris, with the 3 movements of the eye: left, right, and down. And in the next video, you will see you can observe the movements of his eyes and the tiles moving. So these are examples. Yeah, and here is the team that has been working with this experiment. These are 3 PhD students and myself. And here are the co-supervisors of this team. And I would like to end this presentation by paraphrasing the statement of the father of neuroscience that 100 years ago he said, more or less, every man can, if so desires, become the sculptor of his own brain. So I'm happy to receive your questions and comments.
Okay, thank you very much, Professor Molinas. We have now time for some questions from the audience, please. Probably you can see the questions, but I can read them for you.
Okay.
The first one is from Luis Rojas. What are the main challenges with portable technology?
With portable technologies.
Right.
Yeah, so there are many challenges. The question is very general, so it's difficult to know what he wants to know exactly. But the portability for EEG devices is the electrode. I don't know if he meant that in his question. Is in research in the labs, they are using wet electrodes. And in this type of applications for portability and for using continuously 24 hours and long use, we need to develop dry electrode solutions. And the problem with dry electrode solutions is the comfort today, because it's electrode pins are used. And we are experiencing ourselves that these pins are not very comfortable to the user, and they cannot be used for a long time either. So one of the main research challenges in this will be the dry electrode solution that will be the final solution for this concept.
Okay. Well, Professor Pilar Gomez wants to make a question. Probably if she opens her microphone, can do it directly. Or
No, she can't. You have to read the question.
she can.
Yeah.
Okay, then I can read it. Is augmented human brain as brain-computer interfaces?
If augmented human is a brain-computer interface, yes, it is. It is the same thing.
Okay, thank you. Then Luis Rojas again is asking, in the sense of flex EEG, what are the main challenges brain faces?
What are the main challenges there? To come up with a concept, the main challenge is, well, one of our main challenges is the electrode solution, because we need to develop miniaturized solutions. So we enter into the integrated circuits systems on chip, in which we will have a, say, real-time, portable electrode and sensor at the same time. So it's electrode sensor solution. So it has to be small enough. Today, all the solutions are bulky, and they cannot be, as you saw in some of the slides, what we are using here is, here you see the student is wearing a cap that is it's bulky. This cannot be the solution of Flex EEG. These are very uncomfortable devices that you cannot ask the elderly people or children to use for 24 hours. So the ergonomy or the ease of use is one of the main challenges. The signal analysis is a challenge in the sense that we need to get better, more intelligent signal analysis techniques to be able to extract the most important information by using lower number of electrodes. And the brain source reconstruction, that's a big challenge to do it with a low number of electrodes. So we are running very many cases or scenarios with different number of electrodes for different neuroparadigms. And we are encountering ourselves that for different scenarios, we have different number of electrodes, different regions in the brain. And that is the reason why we also make this headset to be movable. That since there are different regions in the scalp that will be needed for different conditions or different applications, then we need to have a movable headset to be able to cover the scalp. So those are among the most challenging aspects of the Flex EEG.
Okay. Now there is a question in Spanish. I'm going to try to translate.
Yeah.
A set of new technologies are converging. Which are the areas that you recommend to be added to the scholar programs? Objects or something like that?
What was the last thing you said? Sorry?
What are the areas that you recommend to be added to the university program?
Yeah. I think the microelectronics has to, the engineering as a whole discipline has to merge with the physical science or the biological science. Because what I am proposing here is nothing else than the merge of engineering with neuroscience or, say, biological sciences. And until now, to be able to develop devices like the one I'm proposing here, we need to have engineering into it. And what type of engineering in this case will be electronics engineering or microelectronics, systems on chips, artificial intelligence, machine learning. And one aspect that I did not, somehow I have underscore was the design of prototype devices, which is something that I'm encountering myself now as a barrier in the design, in the final design of the Flex EEG concept. So in the university, we are not used to have a product design. And the product design can merge with these sciences that I mentioned that are the most obvious ones, like artificial intelligence and microelectronics, are going to, the product design will help to come up with something that can be practical and can be valuable for people to use it. We need to see the side of the user as well.
Okay, thank you. Now from Rafael Gallardo, is the future of BCI in non-invasive technologies or in more invasive and accurate techniques like Neuralink?
Yeah, that's a very good question. I am a ardent advocate of non-invasive BCI, and to be able to continue with this advocation of non-invasive BCI, we need to develop more intelligent science for that and more intelligent technology for that. Invasive BCI is going to get obviously better information, but with a high cost. And I don't see it very much coming without big obstacles in its realization, and will be very restricted to very small group of people. One of the main features of Flex EEG is that we want it to be used by everyone. And we mean it, everyone. Everyone, that today everyone has a smartphone. We would like Flex EEG to be in the hands of everyone. So if it is invasive, it will be so restricted. And that's why probably invasive BCI is going to work, but it is more obvious that because you have to go into the brain and you get better like they do in the research lab with the mice today, then they will do it with humans. Yeah, so I only can say that I advocate strongly for non-invasive BCI.
Okay, thank you. Professor Pilar Gomez again, with respect to the biometric system that you presented,
Yes.
Are you training a model for each possible candidate? What is your experience with subject-independent models?
We have both. We have models for each candidate, and we also have subject-independent models, and we are exploring the validity of these two models. They have worked well for us in small pools. I think the big problem that the biggest obstacles in subject identification will be the larger pools. And that's why we are going in parallel, we are going to test all our models and algorithms and also the neural paradigms in a larger pool from now on. So we have tested only in, say, maximum 100 100 subjects in available data sets, but now we are going to test we are going to acquire our own data, and only then we can see the real accuracy of our system, developed system.
Okay. Well, another one from an anonymous spectator. How they solve the interference of signal emitted by emotions? Don't you make mistakes?
I didn't understand very well the question.
Well, that's the way it is. How they solved the interference of signals emitted by emotions?
By emotions, the emotion of people.
They provoke mistakes, I think.
We are not working with emotion as a neural paradigm so far. I don't understand exactly what is the intention of the question, but maybe he meant that emotion signals can be very much polluted by other things that goes into the mind. Perhaps, I don't know if that is the issue, but I have no experience working with any kind of emotions. The maximum that we are aiming at when we do the subject identification is we would like to also measure the level of stress of the subject. And we would like to perhaps add also the functionality of the ability of detecting lie and truth. But we are not working with emotion, and I'm not very knowledgeable of that aspect.
Okay. Well, another by the same person, anonymous, this, when you mapped the brain of your participant, did you include transsexual people? If so, was there a significant difference between the brain of a transsexual person and a heterosexual person?
No, that's an interesting question. We didn't do that, but when we mapped the brain of the people that was categorized in female and males, we did recognize some particular network or features in the brain for the male and for the female, depending on the neural paradigm that we propose to them. So we observe lateralization of the brain, say left hemisphere for females and majority of right hemisphere for males, depending on the neural paradigm. It's not an absolute answer. So we didn't deepen so much these results, and we are very interested in continuing. So this idea of the transsexual people's brain mapping is a very interesting one. Thanks.
Okay, I have probably two more questions, and there are some more, but this one is from Luis Rojas. You mentioned your daughter was able to drive the drone with little training. Does that mean that the brain signals are more or less applicable for every person? And I'd like to add, it is easier for children to manage BCI?
Yes, that's interesting. Depends on the command that we will use for what the reason I use my daughter for that experiment is because I wanted to send a clear message that this is very simple, and that even people that do not know deeply the science of it, they can do it. And this is why we want to promote FlexEEG for everyone. So everyone can get to understand and test their own brain very early. I'm promoting also a new generation of toys for children by using this concept. So whether children can, it was very easy for my daughter, and that's for sure. And I have done this demonstration in schools, and it was very simple for people in that age. I don't know if it because they have less of other things in their mind when they have a high level of concentration. But depends on the neural paradigm that one chooses. And for example, one neural paradigm that can be used is motor sensory motor region of the brain in which we can lift our arms and use this lifting of our arms, like in the science fiction movies, you know, lifting the arms, just the drone lift up or take off. That neural paradigm is very simple, and it can be very easily captured in the brain by the EEG. The movement of the tongue is another neural paradigm that is very easy, the movement of the head as well. But all these are polluted by other things that go on in the brain. And that is a very person to person, what is in the brain. And we have seen that there are differences between people to people for the same neural paradigm, for the same neural paradigm in different moments, in different days, you know, it's highly changing. But there are very strong signals that remain with very strong features that can be used. That is why this is possible. Regardless of the fact that the brain changes continuously, the choice of the neural paradigm determines how easily or complicated we can make this happen.
Okay, thank you. Well, we have the last one, and all the others, we are going to send them to you, and probably you can reply to them, no? Okay. But now it would be the same, use the flex IG like a cap, then an insert in the brain.
The insert in the brain is an invasive EEG. So I'm not promoting any invasive EEG technology here. So it can be a cap, but I have proposed this headset design because it reminds me of the headset that many people use while walking in the street, when listening to music, you know. It's something that I use this concept just to make it familiar and very simple to use. So I don't know what will be the final design, because as I say, we need to use product design into this to come up with something that it can be user-friendly. I also thought about a cap, a real cap, like can have embedded electrodes inside, like the caps that we use in winter for covering our heads. And in that case, we'll have to have fixed positions. So, but we want to avoid the fixed positions in the skull, because that will mean a high number of electrodes again. So to reduce the number of electrodes, we need to make this headset to be movable. And we will use a small motor that will be embedded in this headset to be able to move this same lace that is on the headset.
Okay, so there are so many other questions, but as I say, we have to finish because of the time. Yeah. And would like to thank you very much to be here with us. We prefer to have you here in presence, but now it's not possible. But the following time, I think we could do that. And in the name of all the organizing committee that you met at the beginning, we thank you again and hope to see you soon.
Thank you very much. And I would also have preferred to be there. You have a great climate there. We are having our winter coming already here. And I'm always very happy to talk about this research, and I'm very happy with all the questions that I got. Thank you very, very much.
Thank you.
Thank you. Thank you, Marta.
So, and all the audience, we will be back again at 3 p.m.
Yes.
Mexican hour. So.
Okay. Then I say goodbye to you.
Thank you very much.
Bye, Marta. Thank you very much.
Well, Marta, I received a message from Moctezuma, Luis,
Yeah,
the student.
yes.
Well, I didn't reply yet, but I'm glad to collaborate in that thing he's proposing to review some thesis or something like that.
Yeah, yeah. Okay. Thank
And
you.
also, we will keep in touch to renew this taste. Well, the purpose of the students to go
Yes.
to the lab.
Yeah, yeah, yeah. I really would like to welcome them, but our situation here is critical. Also, the university is not very flexible.
Yeah, we had to stop now because of this sanitary contingency, but we will be back next year.
We will continue. I will be very happy to